Today we're going to start our second module, and this module deals with more of data analysis. So in the first 2 weeks, what you've been doing is you've gotten your hands on different kinds of computing software, so that if you have data, you have the necessary tools, computational tools, to analyze that data. So the first 2 weeks were spent on the computational tools. Now we would like to move on to the physical tools, which means, given that you have now the felicity of dealing with a computer program, be it Python or the application software, MATLAB, or anything that you fancy. Now what kind of processing is really needed? So now we want to see how do we look at data and how do we infer statistics from that data? Some kind of phenomenon from that phenomenon arises data, and from that data you need to make certain decisions. A decision could be validating a theory, a decision could be proposing a model, seeing whether your data or the phenomenon matches a certain physical model, and so on. Different kinds of decisions are possible. So how do we convert this data into decisions? One D is converted into another D. How does that happen? So that's what we would like to do today. So I'll give you 2 examples of some real data that is gathered in a laboratory, and see how we can write a computer program or a sequence of computational steps to analyze that data. Now I'll go really slow so that everything gets clear as we go along. So suppose I have a set of students and they perform an experiment in which they would like to find out the value of the acceleration due to gravity. And there are 6 or 7 students, and they perform an experiment with identical apparatus, identical techniques, and they come up with a sequence of values of G. Okay? Suppose that sequence of values, let's put this into an array called Y, and let me assume that that sequence of values is given by 9.81, 9.79, 9.84, 9.81, 9.75, 9.79, 9.83. So this is a sequence of values, and this is put inside an array. So what do you gather from this piece of data? What does this data show? Identical apparatus, identical equipment, different students performing the same experiment, maybe at different points in time, but maybe all of them doing experiments in parallel.
There's little fluctuations in values which shows like there is a little bit of error,
Right.
or variation.
So there is some dispersion, some variation from a mean value. That variation could be called flutter, it could be called fluctuation, it could be called scatter, or dispersion, or a spread of values is found. And right now, today, we're assuming that everything is totally random. So there is no systematic uncertainty. So the key is that there is some uncertainty in this sequence of data. So now this is the data that is available to us. It has, before the data step, there is some experiment, some apparatus is built, some idea is tested. But once you have data, you like to make decisions. Now the decision that we have in front of us is what is the best estimate for the value of G. And the best estimate will comprise the result of our measurement ambition. Okay? So now this is our data. So in order to analyze this data, we employ different kinds of techniques. First of all, we would like to plot this data. Okay, so it's just a plot versus the number of experiments versus the trial. So it's not a time series, it's not a plot versus time, it's just a plot in which you plot these values on a graph, and the x-axis is just the serial number. So let's try to do this in Python. Let's see what this data looks like. So if I have a notebook. Let me just increase the size a little bit. Okay, so size बढ़ रहा है कि नहीं? So I create this array of this data. Of course, I need to so this is my data. The mean of this data is this very long sequence of numbers. Okay. Now, at each step, we have to be careful that whenever we do some kind of arithmetic, we calculate the mean. The arithmetic can give rise to a long list of significant figures, but we really have to truncate our value. So, if someone asks you what is the mean value of g for this case, you do not want to quote the number of significant figures to be greater than the least number of significant figures available in the original data. Right? So the original data has 3 significant figures. So the best you would like to quote is 9.80. Okay, you do not want to be more precise than the least precise of the inputs. Okay, so this is really important. So what we could say is that you want to round off this number, the mean value, to say 3 or 2 places after the decimal. 9.80. So there is also a method to show this 0 in Python. You can write a code for that. So now I've described the length of this array to be n, and I've done I've written another for loop to calculate the mean here. Okay, so I hope you all understand how this for loop works. I initialize a variable for some, and then I take some dummy variable, call it number, and put it in the range of the length of y, and I keep on adding the previous value of sum to each element of the array, and then I take the final sum that is created after I've gone through the array and divide by the length of the array to get the average. So this is another way of computing the average, and this is the sequence of steps that this computer program follows. It keeps on adding the values in the array, which are the values, those values that you have on the blackboard, and then finally you find out. You take the sum, which is this last value, and you divide this by 7, which is the length of the array, and this is the mean that you get, which matches the mean that you get from the routine that is available in Python. Alright, so now we have a mean available to us. So the first thing that you would like to do is you would like to find out this average. This is a really important number. But beyond this average, you do not know what the spread of the data is, but you have the data in front of you. So now you would like to find out the spread of this data. Now one measure for the spread of this data is called the standard deviation. Okay, and the standard deviation is found in the following fashion. You take each value of y, each value inside this array, let's call it by I, and from it you subtract the mean of all the data, and then you take each one of these differences. This difference, by the way, is called the deviation or dispersion. How far is a particular value from the mean? It's a measure of the spread. So if you compute this deviation for the first number, it tells you how far you're from the mean. You can find out how far is this number from the mean. So you take all these deviations, you square each one of them. Okay? And you take the square because some of the deviations could be positive, others could be negative. Some numbers could be bigger than the mean, others could be smaller than the mean. And you do not really care about whether you're above the mean or below the mean. You just care about how far are you from the mean. That's why you take the square. And then you sum up over all of these values over I. And then you divide by n minus 1, where n is the total number of the length of the array, and you take the square root of this. So this number is called the standard deviation of this data. Okay? If n is really large, say if n is about 50, 60, or you have large number of values at your disposal, then n minus 1 will be roughly equal to n. So it doesn't matter. But these differences become important when you have small amounts of data, say less than 8, 9, or 10 values. But this number in itself is called the standard deviation. It's so important, I would like to write down the name here, standard deviation. Okay, and it is really a measure of the spread of the data. How far is any data point away from the mean of the data? It tells you the dispersion. So let's write a program that achieves this. So I import another library, the math library, because I need to find out square roots. And then I write this piece of code. Once again, I initialize a variable, which is the cumulative sum, to 0. I put in a dummy variable, and this number goes from 0 to the entire length of this array. And for each number, I take the difference of that number from the average. This y average has been computed prior to this loop. I take the square of each of these numbers and add this value to the previous sum. So I keep on accumulating the sum. The variable keeps on growing. Finally, I divide this sum by n minus 1 and I take the square root. So this gives me the standard deviation of y. Alright? So the standard deviation of y, if I would like to look at its value, it's this value here, 0.03. Can you see from the back? पीछे से नजर आ रहा है? या नजर आ रहा है? या बड़ा कर दूँ? ठीक है. So this is a standard deviation, 0.03 meters per second square. Now instead of the standard deviation, there is in addition to the standard deviation, there is another important, really important variable that tells you something else. So let me see if I first of all, if I were to plot the data, let's plot the data. So this plot here let's look at this data. So this is a plot of the data. See how I've plotted it. I have a variable called index2. So I define a variable index2, which is simply the sequence of numbers from 1 to 7. Okay. I could also have used the command linspace, np.linspace. Probably you've already seen that in one of your prior lectures. So this is just the index of numbers. So this is measurement number 1, data 2, data 3, and so on. So int2 is just an index. So I create this index, and then what I do is I also want to draw a line at the average. So I take the average and create an array which has 7 elements. Each element is equal to the average, so that I'm able to make a plot of it. So I take my average value and just repeat that average value 7 times by multiplying it with an array of ones. Okay? So this is my y-average array. And if you look at the values in the average array, it's just the mean of these values repeated 7 times. Because I eventually want to make a straight line at the average value and compare my data points with respect to that average value. Finally, I plot all of this. So if you look at this graph here, so I plot y versus index 2. These are my data points. And since these are discrete data points, I plot them as red objects, red circles. Because these are discrete data points, I don't want to draw a line that connects these points. Because these are discrete points, they should be respected as such. However, I would also like to make on the same grid another plot. And that is a plot between the average value, which is of course a constant. The average is just a constant, and I draw a line for that constant. So this is this blue line over here. So now this is a view of the data that we have in front of us. Now in this view, we have plotted the average of all of our data, and we now see the scatter of all the data points about the average. Some points are above, others are below, and none of the points is actually equal to the average. Okay, so the average need not necessarily traverse the data set. The average could be something different from all the data points, as is seen in this case. Now all of these points are spread about the average somehow. What we would now like to do is we would like to see what is the standard deviation, how does the standard deviation appear on this graph, and how does another quantity which is called the standard error appear on this graph, and what is meant by standard error. So first of all, Abhi, a quick question, any question here? Alright, so this is really simple. So the next step would be to, if I were to ask you, by looking at this data or looking at this plot, you always have to draw a plot, by the way, for most of your experiments and most of your experimental work, because without plots, without graphs, you cannot make decisions. You cannot draw inferences from the data. So by looking at this plot, if I were to ask you, what's your best estimate for the value of G, what would your answer be?
1 and 4.
9.81, which is equal to what, the average?
Closest to that.
Closest to the average. But how confident are you about this? So there has to be some confidence that is put into your answer. So one has to define confidence intervals, confidence ranges. Yes, please.
What if we can use standard deviation and compare the value which has least amount of difference to the mean value?
And you just pick that value as your real value. Why not the mean itself?
Like we can see the amount of error in the value comparing with standard deviation.
So, but one would say that the mean is a good estimate, but when you make a measurement and you want to find the best estimate of some parameter that you're measuring, what you really do is you would like to say, my best estimate for this parameter is some value, but this could lie in this particular range with a certain confidence level. That's what you would like to do. So you would like to have a best value, a range, and the confidence with which you can say that your value is hovering in that range with some confidence level. So you need a value, you need a range, and you need a confidence in that range. Or you need a value and you need a confidence interval. So these are two things that you would like to know: a value and a confidence interval. So now that's what we would like to analyze. What the standard deviation does is, I would now like to plot this standard deviation on this graph. The standard deviation would really be a band of values, because the standard deviation as you calculated is about 0.03 something. So this imposes a certain band. Let's see what that band looks like on this graph. Okay? From there we can tell what the standard deviation really means. So what I would now like to do is, I've already calculated the standard deviation. Here is my standard deviation. And now I would like to plot all of this. So if you look at this piece of data, I want to draw two lines about the mean. So I have a line for the mean, and I want to draw a line above the mean and a line below the mean. And the line above is the mean plus the standard deviation, and the line below is the mean minus the standard deviation. So now instead of a line for the mean, I want to have a band. And the band is mean plus the standard deviation and the mean minus the standard deviation. Okay? So that's how I define a line for the standard deviation. Okay, this is the standard deviation multiplied by a sequence of ones. This will give me a straight line. Now forget about this second thing. I'm going to explain this second thing in a minute. Standard error in a minute. So now I invoke another figure, and now I want to draw a band. So I use this function fill between. Index 2 is my x-axis. I want to plot one line, y average plus the standard deviation, y average minus the standard deviation. And I want to fill in this with some color, with some opacity, which is called alpha in Python, put in limits for y. And then I also want to plot the points as well. Alright, so I run this piece of code. So this is what I get. So now in this graph, I have this dark blue line is my mean, and this band, this light blue color is my band, which subsumes the standard deviation, plus minus, about the mean. Now if you look at the data points are scattered about this band. Some of the points lie within the band, and some of the points lie outside the band. The standard deviation is something that if the probability for large data sets is that if you pick a particular point, any point from this data, any point, pick one point, the probability for large data set that one point that you picked lies within this standard deviation band is about 68%. Okay, so this is how we define the standard deviation. But of course, if you look at this standard deviation, sorry, this is a standard error. Excuse me. Right. Sorry, this is the proper plot. This is it. Sorry. गलती से आगे चलो. This is the plot data, average and standard deviation. जरा आगे चला गया. ठीक है? समझ गए? So I run this function. This is my graph. This is the standard deviation band, the band for the standard deviation. Mean, this upper limit is mean plus standard deviation, this is mean minus standard deviation. Some points lie within, some points lie outside. On average, if you pick a point from the data set, 68% probability would be the probability that this data point lies within this band. Okay? And it's especially true if you have a large data set. But some points invariably lie outside this band. Okay? So that's very possible. But the standard deviation really tells you this particular facet is that if you have a data point from your data set, the probability that it lies within plus minus standard deviations is about 68%. ठीक है? ये standard deviation का मतलब है. और ये एक figure है जो आपको dispersion बता के देगा. अब इससे अगर आप पूछें आप कि भाई what is your best estimate for the value of G? So you really need to know how confident are you about the mean, right? So is the mean a good metric or an identifier for the best value? Yeah, right now not, it can have, but let's ignore the, even if we don't have outliers. So we need, the mean remains the best estimate for our parameter that we want to find, but we need to assign a certain confidence with it. The mean could also be uncertain. How uncertain are we about the mean? That's the next question I would like to answer. So this scatter, if the scatter is large, if the standard deviation is large, which means the mean could be uncertain as well. But if you have a large number of data points, so the simple question with which you would like to address this problem is, if I increase the number of data points, will your certainty in the mean increase or decrease, or it should be oblivious? Increase. So if you have more points, you will be more certain about the mean, and you will be able to say that the mean is in fact a true representative of the true value of G. It's your confidence in your best estimate is going up if you increase the number of data points. So how good is your conception about the mean? So you define another metric, and you really like to call it the standard error in the mean. So now you want to define a metric which is associated with the mean itself, and we call it the standard error in the mean. Okay? So just imagine I have a box in which I have a large number of balls, very large number of them. And on each ball I've written some number between 1 and 9, say. Some number, and I take out 10 balls from this object, and I find those numbers and I find out the mean. I'll get a mean. But then I put those 10 balls back into the box, and I shuffle the box again and take out 10 numbers again. So I can get a sequence of means. Each sample that I get out from this large population of balls has a mean and a standard deviation. But now if I repeat this experiment a large number of times, I can even get a standard error in the means, or a standard deviation in the means. I can find out the standard deviation in the means itself. The standard deviation in the means is called the standard error in the mean. That will tell me how confident can I be about the mean itself. So I really need to find out the standard deviation in this sequence of means. And this is called the standard error in the mean. Okay? Now we've uploaded some documents on our website which give you the derivation of this formula, but let me state the result of a formula that allows us to compute the standard error in the mean itself from the standard deviation of the data. And that formula goes as follows. So I take S and I divide this S by the square root of the number of data points. This value is called the standard error in the mean, sigma m. So if I increase the number of data points, my confidence in the mean that I've calculated goes up, which means the standard error in the mean goes down. If this n goes up, the standard error in the mean goes down. Getting more data which is spread around the mean does not change the standard deviation if the errors are totally random. I can get more and more and more data, but that will not change the standard deviation of the data because the data is spread anyway. However, by looking at a large set of data, computing the mean computed from a large set of data will have a smaller uncertainty. Okay, and that's what this object called the standard error in the mean tells us. Mathematically, the standard error in the mean is a standard deviation in means computed over and over again. So this is the formula. Now you can tell that increasing the number of data points is going to decrease the standard error in the mean. That's why in experiments, if you have noisy data, if you repeat the experiment and keep on adding the data or averaging the data, it's possible that the noise goes down. Signal goes up, which means the signal to noise ratio goes up. So when you're doing very sensitive experiments, you want to measure low voltage of the order of nanovolts, picovolts, small currents, very small deflections of the order of microns. You generally want to repeat the experiment a large number of times, so that, and then you add up all your data, average it, and then you'll find out that small futures start appearing because the signal noise ratio goes up, the standard error in the mean goes down. This process is called signal averaging. Okay, so this is a technique that's always used in experimental physics laboratory. So now you can tell that the standard deviation has some value. What about the standard error in the mean? That's smaller generally than the standard deviation because n is larger than 1. Okay, so for our data, let's look at the standard error in the mean. Okay? So now how do I calculate the standard error in the mean? Look at this line of command here. I have the standard deviation. I've already calculated the standard deviation of the data. And from that standard deviation, I want to divide this by the square root of the number of data points. So I divide this. That's why I imported the math library, because I want a square root. I take the square root of the number of data points. Alright, so this will give me the standard error in the mean. Now here is the standard deviation 0.03, the standard error is 0.01. It's smaller than the standard deviation. Got it? So now we would like to plot the band associated with the standard errors. And that band is going to be tighter than the band due to the standard deviations. Okay? So now if I were to plot the standard, so this is, remember, this is the standard deviation band. The points are scattered around the mean, and about 68% of the data points lie within this band. And if I look at the standard error, so here I'm plotting the standard error. This is what I get. The standard error, the band is tighter. So now more points fall outside the band. And if I had more data points in this graph, this band would be even tighter. And we want tighter bands, because a tighter band will tell us that this mean lies within this band with a high degree of confidence. A tighter band is good for us because we'll have more confidence in the mean that we've calculated, even though the data is spread out, right? So we want tighter bands, which means we want more data points. But remember that having more data points is not always possible, because experiment could be expensive, it could be time consuming, it could be laborious, it could be very hard to do an experiment. Some experiments are years long. Particle accelerator experiments might take 2 or 3 years, a single experiment. So it's not always practically feasible or technologically feasible to have longer experiments. Right? Students don't want long experiments either. But nevertheless, sometimes you have to do longer experiments, gather more data, so that your bands in the standard error in the mean go sharper and sharper. And we are then more confident about your mean. And you can tell that your mean is a true representative of whatever true value of the parameter is. Okay? अब एक सवाल मैं आपसे पूछना चाहता हूँ कि I'm talking about confidence. Can we quantify this confidence? I'm confident about saying that this true value lies within this band, but how much am I confident? I can assign a quantifiable confidence level to this statement. I'm confident by 50%. There's a 50% chance that the mean can still lie outside this band. I'm confident by 90%, which means that there's still a 10% chance that the true value can lie outside this band. Okay, so I need to quantify this statement. So let me move to the blackboard for trying to answer this question here. With the quiz सवाल जी.
Does the band represent a mean lies in this या फिर a true value lies in this?
The mean is a representative of the true value. So you can say either the mean lies in this as well as the true value lies in this with a certain confidence level. Okay? Because you cannot have any other estimate but the mean to be a representative of the true value.
But कोई आपका भी हमारे के fact के कोई
outliers उनको डील करने के और statistical tools, ठीक है? और अभी तक हम सिर्फ random errors को देखते हैं, random uncertainties को देखते हैं. By the way, just let me be very clear. Uncertainties are the holy grail of doing experiments, of measurements, and they're not mistakes. Errors or uncertainties, they're not mistakes. These happen all the time. So if I have an object and I throw this object, right, it falls on the ground and I time it, and I do this again and again, I will get a scatter of data. And this is not a mistake. I can be more precise, more careful, more meticulous in doing experiments. I can use more precise equipment, but still there is always going to be some uncertainty. So you need to identify what the uncertainty is and quantify what the uncertainty is. That's what you need to do in a measurement laboratory. Okay? Yes, please.
I have a question, but if there is some error in the band itself, can there be any error in the band?
There can be errors in the band itself. So you can calculate the standard deviation in the standard error as well. But then it becomes smaller and smaller and smaller. These higher order moments become smaller and smaller. Okay, so you have to stop somewhere. Okay. So now what I want you to do is I want to talk about confidence.
Would be the true value that we're trying to find. If you go decrease higher and higher.
We're trying to follow the true value.
No, but like.
But our mean is the best representative of the true value.
Yeah, but like if we keep calculating, what would be the numerical value that we eventually get? Because the range will get smaller and smaller, right?
So eventually we'll get the mean. We can't say whether that mean is really the true value because of accuracy reasons. Because your instrument could be inaccurate, it could have a systematic error. So as humble experimenters, we can only be confident about the mean and we can put bounds on the mean. And then we have to use our judgment as a physicist and as an engineer whether that mean represents the true value or not. Okay. So what we would like to do now is we would like to talk about confidence intervals. So our best estimate for, say, capital Y is some hypothetical true value. Hypothetical. We never know what the true value is. But this is some hypothetical true value that we're chasing. Now what we have with us is Y prime. This is the best estimate for Y, capital Y that we have. Okay? And what we could say is that if we have, let's denote the standard error in the mean is sigma m. Okay? So if I were to say Y plus minus some numerical value, let's call it t, some number t, plus minus t times sigma m. Suppose I kind of want my mean to be a representative of the true value and I want to have a 95% confidence level. Suppose I want a 95% confidence level. Okay? So my confidence level that I need is 95%. So for this confidence level, I need a certain value of t. So this is the band that I want, above and below the mean. Now this t depends upon the confidence level that I need and the number of data points that I have. Okay? So let me draw, and where does this t come from? So if my number of data points is larger than about 20, then for a confidence level of 0.95, my t is roughly equal to 1.96 or 2. So what does this mean? So if I have a large number of data points, 20 or more roughly, then, and I want to know a confidence, I want to have a confidence of 95% in my estimate, then for that 95%, I choose a t of about 2, which means I find the standard error in the mean for those data points, multiply this with 2, and then this gives me the band in which my true estimate lies. If my n is, say, less than 10, for the same confidence level, 0.95, my t is roughly the same as under root n. So these are just numerical estimates. And this t is coming from a probability distribution function, which I don't think you've studied so far. You haven't studied probability distribution functions, but it comes from a particular probability distribution function which is called the student's t distribution. You don't need to know about this, but you just need to remember that this t depends upon how many points do you have, which is also called the degrees of freedom. How many points do you have and what confidence level do you want? Okay? So let's look at a particular example. So by the way, if you have fewer points, like in this case we have fewer points, our points were just 7, then your t is just the same as square root n. And if I look at t times sigma m for n less than 10, this is under root n, and my sigma m, as you know, is s over under root n. So this band, the 95% confidence band, becomes the same as the standard deviation band for fewer points at the 95% confidence level. So let me give you an example of the G. ये वाली ये बैंड है ना कि इस मीन के इर्द गिर्द कितना बड़ा बैंड बनाना है, और उस बैंड के अंदर मैं चाहता हूं कि 95% कॉन्फिडेंस के साथ मैं कह सकूं कि मेरी ट्रू वैल्यू इस बैंड के अंदर लाई है। ठीक है, तो ये बैंड की दो लिमिट्स हैं, अपर लिमिट और लोअर लिमिट, और वो बैंड कितना बड़ा होना चाहिए? द बैंड डिपेंड्स अपॉन द स्टैंडर्ड एरर इन द मीन, but it's some multiple of the standard error in the mean. That multiple is t. How do you find t? T is found from a numerical code or from the student's t distribution. If you want to read about this, you can read about it. But these are the rules of thumb, and we can write a computer code, and I'll share that code with you, in which you can automatically calculate that t for any number of data points. Okay, so let's try to do that. So if I now what I would like to do, I would like to calculate that t for my particular data, the value of t. What numerical factor do I attach to the standard error in the mean to compute the bands, the 95% confidence levels? So in order to compute that t, I need a statistical function which is called the percentage point function, PPF. It's an advanced statistical concept, but I need a particular library from the scientific Python library called statistics. So this is how I compute that t. Okay, and you can kind of reuse this code whenever you want. So I take stats.t, I take this routine and this function t, and the PPF, the percentage point function, and here I have 1 plus the confidence, which is 1.95. 1 plus the confidence, 1.95. I divide it by 2. Suppose I have a large number of data points, 10,000 or thousands of data points. Then this value turns out to be 1.96, as I mentioned over here. Okay? So for a large number of data points, if you want to find 95% confidence level, I take my standard error in the mean and multiply it with 2. Okay? For fewer data points, I have to explicitly calculate what my t should be. So for 10,000 points, this number is 1.96, and for 7 points, the points that I have, this number is 2.36. Okay, so if I take the mean of my data plus 2.36 times the standard error that I've just calculated in previous prior to this, within this band I can be confident with a degree of 95% that my true value is going to lie within this band, or my mean is bounded to lie within that band with a confidence of 95%. And that's how I quote my uncertainties in all experiments. Let me just show you the data and then I'll take questions. So now I'm going to plot this. So let's look at this piece of code. So first of all, let's do a computation. So what I've done is I find out the t value, the critical t value for my data points. I have 7 data points. So really, in the code I put 7 minus 1. I take the number of degrees of freedom, which is 1 smaller than the number of data points. Okay? So I take 7 minus 1 as the second argument of this function. The first argument is 1 plus the confidence that I need. 0.95 is the confidence, so 1.95 divided by 2. This gives me this thing. You see, this is the standard error. I multiply it with the critical t value that I find from the point percentage function. Okay? So so here first of all I quote the numerical t value for my data, which is 2.45. Then I quote my final result, which is the outcome of my measurement. First of all, I mention the average value that I get. I put this average value up to 2 significant figures, 9.80, 3 significant figures, 2 places after the decimal, plus minus, and this is my t times sigma f. It's 0.03. And this 0.03 is actually this standard error multiplied by the t that I find from the point percentage function. So my data, my final measurement outcome would be, and I would state in clear words and I would declare that the measured data is 9.80 plus minus 0.03 at the 95% confidence level. This is a complete measurement outcome. So you have your best estimate, which comprises an average, it comprises a band, and it comprises a confidence level. And generally measurements are quoted at 95% confidence level. And do keep in mind that the number of significant figures, this is an uncertainty in a way. The number of significant figures here is generally 1. There's only one significant figure. That's this 3 here. And the position of this significant figure with respect to the decimal 3. So the truncation, the rounding off of the significant figures is identical for the mean value and the standard uncertainty that you quote. A plot of the data, the average, and the standard error, just sigma m. The standard uncertainty will be about double this band, double this size, because our t is about 2.35. Okay, so this is just the standard error that we plotted previously. Now we want to plot t times the standard error, which is our standard uncertainty, because we are working at 95% confidence level. If you were working at a 68% confidence level, this would be enough. We're going to work at the 95% confidence level, which is customary in metrology, customary in measurement schemes. So now we plot at the 95% confidence level. This band gets inflated from the standard error band, because now it's roughly twice the standard error band, or 2.35 times the standard error band, because t has a value of 2.35. Now in this graph, this is our mean. We can say that with 95% confidence, our mean lies in this band, which is also tantamount to saying that our estimate for the true value, as far as we can tell, barring accuracy reasons, barring rating reasons, barring systematic uncertainties, is within this band to confidence level of 95%. There's still a 5% chance that the true value lies outside this band. Got it? अब समझ आए सारी बातों की? अब आप सवाल पूछो।
एक मेरा सवाल ये था कि हमने 1.95 को 2 से क्यों डिवाइड किया? जो कॉन्फिडेंस लेवल है।
There was
मुझे समझ लो आता है ये हम 95% और 68% इसलिए यूज करेंगे बेल कर्व के लिए बिल्कुल क्लियर है बेल कर्व में मीन के ऊपर और नीचे स्टैंडर्ड डिवीएशन के अंदर हो तो वो 68% एरिया लाई करता है so we want to refer everything back to the bell curve because there are different kinds of uncertainties there are different kinds of probability distributions the final results that we quote should be in a manner that they are independent of what kind of instrument is used what kind of probability distributions are used everything has to be referred back to the normal distribution of the bell curve so all of these values are naturally stemming from the bell curve the student t distribution for large value of n is equal to it approaches the bell curve अच्छा अब एक बड़ी मजे की चीज है ये सारी हमने अनसर्टेनिटीज की हैं ये जो स्टैंडर्ड एरर निकाला है ये स्टैंडर्ड एरर क्यों था कोई तरीका है कि स्टैंडर्ड एरर 0 हो जाए कोई तरीका ये स्टैंडर्ड एरर नॉन जीरो है क्यों क्योंकि स्टैंडर्ड डिविएशन नॉन जीरो है तो स्टैंडर्ड डिविएशन नॉन जीरो क्यों है क्योंकि पॉइंट्स फ्लक्चुएट अबाउट द मीन so this variation this random uncertainty gives rise to these uncertainty bands gives rise to all of this uncertainty the final standard uncertainty that we quoted is because the values do not lie on a straight line they have some fluctuation हमेशा ऐसे होगा तो ये जो अनसर्टेनिटी जो हमने बात की जिसे हम स्टैंडर्ड अनसर्टेनिटी कह रहे हैं स्टैंडर्ड डिविएशन है जो स्टैंडर्ड एरर को कॉज कर रही है इस किस्म की अनसर्टेनिटी व्हिच इज ड्यू टू द डिस्पर्शन ऑफ द ओरिजिनल डेटा दिस इज कॉल्ड टाइप ए अनसर्टेनिटी टाइप ए अनसर्टेनिटी okay so this is one of the two major kinds of uncertainties but there could be other uncertainties as well for example the students calculated the 7 values of g 7 students calculated 7 different values of g now for each of the students now this is a very important and subtle point for each of the students he or she can be uncertain about his or her own value as well. And where does that uncertainty come from? Could come from different sources. The measurement instrument has a finite resolution. It does not have no instrument has an infinite resolution. There is a least count, in other words, for every instrument. That's called the resolution of that instrument. Resolution का मतलब उर्दू में यह है कि आप कितना छोटी चीज को देख सकते हैं, कितने दो करीब चीजों को रिजॉल्व कर सकते हैं, फर्क कर सकते हैं, which means what is the smallest that you can measure. So there is a resolution for every instrument. Then there could be the accuracy of the instrument. When a manufacturer makes an instrument, lab is about instruments. When a manufacturer makes an instrument, the manufacturer quotes that my reading from our instruments will be accurate up to 1%. Or if I'm using a voltmeter, every reading will be accurate up to half a volt. Suppose you're reading values on an analog scale. Now you can be uncertain about where the pointer actually lies. Because either the scale is too small, the pointer has a finite size, and you don't know where it actually lies. So there is always uncertainty even in a single measurement that a single experimenter is doing, and that has nothing to do with the scatter. Okay? So if you take your smartphone and look at your stopwatch, there is a least count on that stopwatch. So there has to be uncertainty with the value of time that you measure. If I time something with a stopwatch, there is some response time that is associated with that process. So all of these values, all of these matters indicate that, lo and behold, even a single measurement will have an uncertainty. That uncertainty associated with a single measurement is called a type B uncertainty. So far we haven't seen type B uncertainties. But then uncertainties are like transferable currencies. All kinds of uncertainties, no matter what their source is, they all combine together to give you a total uncertainty. So far you've seen type A, what about type B uncertainties? So let me give you an example. Of G, that is student measures, has an uncertainty, a type B uncertainty of 0.2%. 0.2%. ये बात बड़ी ध्यान से देखने वाली, क्योंकि हमें लैब में करनी और आपके अगले इसको हमने प्रैक्टिस भी करनी है, फिर आपका एग्जाम भी होना है, जरा इसको गौर से देखना है. Suppose every value of G that is measured has in itself a 0.2% uncertainty due to some causes, due to accuracy of the instrument, due to least count, due to resolution, due to whatever the process is, whatever the cause is. So now what I do is, I want to plot the data with the type B uncertainties, and I want to plot the standard deviation line as well, standard deviation line of the data as well. So what I do is, I now assume that there is an error in each Y value, and that error is a type B uncertainty is 0.2%, 0.002 times each value that you get. So I want to plot this data with error bars. So all the plots that you make must be with error bars. Okay? So I take this data, and first of all plot the raw data Y, but associated with this Y, I plot the error bars as well. And then I also plot the standard deviation line. Remember? Standard deviation line of the data. So when I plot this, this is what. Now this is your first introduction to error bars, maybe your second. So now this is the mean value as before. These are my data points, but associated with each data point is a type B uncertainty, which has been devised by an error bar. And these bands correspond to the standard deviation. Okay. Now if you notice that will these type B uncertainties have any contribution to the final standard uncertainty that you've calculated? I give you 2-3 minutes to think about this. Let me switch to Urdu. पहले हमने देखा था कि हमने कुछ टाइप बी अनसर्टेनिटीज कंसीडर नहीं किए थे. हमने स्टैंडर्ड डिविएशन देखी, उससे स्टैंडर्ड एरर निकाला, स्टैंडर्ड अनसर्टेनिटी निकाली उससे. ठीक है? अब हमारे साथ ये मसला है कि हमारे हर पॉइंट डेटा पॉइंट के साथ एक टाइप बी अनसर्टेनिटी वाबस्ता है. अब मेरा आपसे ये सवाल है, स्टैंडर्ड डिविएशन डेटा का तो वही है, फॉर्मूला में स्टैंडर्ड डिविएशन का बदल नहीं रहा. अब मेरा आपसे ये सवाल है कि जो फाइनल स्टैंडर्ड अनसर्टेनिटी है उसमें कोई रोल है इस टाइप बी अनसर्टेनिटी का? वो कुछ चेंज हो जाएगी? अब मैं मीन के बारे में ज्यादा मुतमईन हो जाऊंगा, कम मुतमईन हो जाऊंगा, या फर्क नहीं पड़ेगा? मेरा कॉन्फिडेंस लेवल चेंज हो जाएगा, या फर्क पड़ेगा तो बहुत थोड़ा पड़ेगा? मैं 2-3 मिनट देता हूं, जस्ट थिंक अबाउट दिस क्वेश्चन and then I'll seek answers to you.
So because there is also spread for each point, so we'll have to consider range for each point, which would mean that the standard deviation would also have to be sort of a range, which would further increase my confidence level about the deviation.
Right. So here we have to make a judgment call. Here the type B uncertainties, just look at the type B uncertainties. That's why it's so important to plot and visualize data. Tables are not enough. Everything has to be on a computer. You need to have a graph in front of you. So this is my standard deviation band. And this standard deviation band is caused just by the fluctuation of the points about the mean. Right? Now if you look at each of these points has an uncertainty associated with it. So this is an uncertainty associated with point 1, 2, 3 and so on. Now if you look at these error bars, most of them, with some exception, with some minor exceptions like this point, most of these points lie with the error bar, even with the error bars, the points lie within the standard deviation. Correct? So this wholly and solely lies within the standard deviation band. This mostly lies, just about 5 or 10% is outside. This is about 20% inside, wholly solely inside, almost wholly solely inside, 50% inside. This, however, is 0% inside, and all of it is outside. But on average, on a whole, most of these error bars lie within the standard deviation. If I were to increase the or decrease the standard deviation, the type A uncertainty a bit further, make it 0.1%. 0.1%. This is what I get. Even further. See? So I've decreased the type B uncertainties even further. Now all of these uncertainties almost lie within. So out of the 7 points, 5 lie wholly within, 2 lie wholly outside. So even if I were to take into account the type B uncertainties, most of the data lies within the standard deviation. The standard deviation already takes into account the fluctuation of the data. Let me finish. Right? So if I were to include the impact of these fluctuations of each data points, that would be double counting. I don't want to do that. So I make a judgment call. I look at my type B uncertainties and compare it with the original standard deviation of the data. And if a large number of data points with their error bars lie outside, say 50% of them lie outside the standard deviation, I then have to include the impact of type B uncertainty. Otherwise, I can ignore. Or the impact will be so small that I don't want to do the algebraic or numerical hassle of calculating it. So I have to do a judgment call. So if these fluctuations in each point are such that they are subsumed within the standard deviation band, subsumed उसी के अंदर जम हो गए, उसी के अंदर गिर गए हैं सारे. So I don't need to take into account the fluctuations of each data point. Got it? You get a question?
Sir, even though we are seeing like with the error bars on points still lie within standard deviation of data. So what about these points lying in standard error of data? Will it still be within standard error of data?
Not necessarily, but the standard error is already calculated from the standard deviation. So if something is not going beyond the standard deviation, you don't want to do an extra calculation of that. Okay, the standard error is calculated from the standard deviation. Okay. So if the standard deviation is already taking care of type A uncertainty because it's a spread of the data, and additionally it's taking care of the type B uncertainties as well. However, if these data points have a large type B uncertainty, each one of them, say 2%, right? So I have a large uncertainty of 2%. So now I would like to do a 2% type B uncertainty. Let's look at what the data looks like. And so each time we want to compare what the data looks like with the error bars with the standard deviation of the data. So standard deviation is type A uncertainty, and we brought the error bars which are type B uncertainties. Remember, standard deviation just tells us the type A uncertainty because that's due to the fluctuation of the data about the mean. So now if I plot with a 2% uncertainty, I get this data. This is the data set that I get. Now, if you look at this data set, the points are still the same, the mean is still the same, nothing changes. This is my standard deviation band, but now the points have a very large type B uncertainty. So it is, I would say, it's not allowed, it's impermissible, it's forbidden not to take into account the type B uncertainty. Type B uncertainty has to be taken into account. So now there are two kinds of uncertainties that are combining, fusing together. The fusion of uncertainties. One uncertainty is just due to type A, the scatter of the points above the mean, which is why these points lie above and below the mean. That's type A. And the other is that each point has a large swing in it. So type B uncertainties now also need to be considered. So now with the standard deviation, the standard error in the mean can be calculated, but in order to find the final standard uncertainty, one really needs to take into account the standard error and somehow fuse it with the uncertainty that is coming from the type B uncertainties. Right? तो वो कैसे आएगी? तो दो तरह की अब standard deviations होते हैं in a sense. So now you have to talk in terms of very universal terms. One standard deviation is coming from the scatter of the points, and one spread of data is coming from the type B uncertainties. So both of these standard deviations will then combine to give you an overall total uncertainty. So we already know how to compute the standard deviation. So now let's see how do we compute the impact of these type B uncertainties. Standard deviation. From the standard deviation, we can calculate the standard error in the mean. So far we've done this type A uncertainty calculation. Now, what would the mean be? What would the mean be if we included type B uncertainties? The mean could be totally different, right? So now let's look at the standard error in the mean in a sense arising from the type B uncertainties. The mean could be wildly different now. ठीक है? अब mean कुछ और हो सकता है. Mean यहाँ भी हो सकता है, यहाँ भी हो सकता है, इधर भी हो सकता है, इधर कहीं भी हो सकता है ना. Mean की fluctuation बढ़ गई है. Standard error in the mean बढ़ गया है. ठीक है? तो वो कहाँ से हम calculate करेंगे? तो उसका तरीका ये है कि now you use another concept called the propagation of uncertainties. How is the mean calculated? You take any value of y, sum of all the values of y and divide by n. Correct? So if I expand this is y1 plus y2 plus y3 by 7. So this is the mean that you just calculated, and from this mean you calculate the standard deviation, you calculate standard error in the mean. But this is type A. Standard deviation, standard error type A. Now I want to do type B calculation. Now the type B calculation means that there is some uncertainty in this y, some uncertainty in this y, and so on. So with each y, with each of these values there is some uncertainty, right? So there is some uncertainty associated with this u of y1, some associated with this u of y2, u of y3, so on, u of y7. So if all of these values are uncertain, this mean will also be uncertain. Now you are adding large number of random variables together. ठीक है? तो इसके अंदर भी कोई uncertainty आ जाएगी ना. If there were no uncertainty, no type B uncertainty, you get a precise value of this mean. Precise value आती है. अब नहीं आएगी. You now your type B uncertainty. So how do I compute the error in the mean? from the knowledge of this formula and the uncertainties in sorry u of y1 is the uncertainty in y1. ये इसके एरर बार है, ये इसके एरर बार एंड सो ऑन. तो अब ये सारी चीजें अनसर्टेन होगी ना, तो ये भी अनसर्टेन हो जाएगा. तो हमने देखे थे व्हाट इज द अनसर्टेनिटी इन द एवरेज वैल्यू ऑफ y दैट वी कैलकुलेट. बहुत ज्यादा अनसर्टेन, ये गलत बात है. बट अनसर्टेनिटी पॉजिटिव भी हो सकती है, नेगेटिव भी हो सकती है, और बहुत वाइड रेंज उनकी अनसर्टेनिटी होता है जीरो होगा एवरेज. ऐसे तो नहीं होगा.
जैसे अगर इसकी 2% हो तो हम 1.2 एक बार लेकर दूसरे का 0.8 लेके फिर मल्टीप्लाई भी कर सकते हैं.
कर तो बहुत कुछ सकते हैं, लेकिन क्या चीज ठीक है. तो एवरेज तो देखिए ना, वो तो
प्लस माइनस यू है तो फिर प्लस यू की इक्वल सारी लाइन पे माइनस यू की इक्वल सारी.
देखो यहाँ पे देखो, अगर ये पॉइंट दरअसल यहाँ लाई कर रहा होता है, क्योंकि इस पूरी रेंज में कहीं भी पॉइंट लाई कर सकते हैं. ये यहाँ होता है, ये यहाँ होता, इनके एवरेज रेट जीरो आ जाता.
नहीं, लेकिन अगर हम ऊपर वाले तो पहले लें,
इसकी ले लें, फिर यहाँ ले लें, फिर एवरेज वो भी जीरो हो सकता है. तो ऐसे तरीके में ना यू ऐड, first of all you need to propagate uncertainty. This is called propagation of uncertainties. So these uncertainties in these primary values, they propagate into a derived value. So you have to look at the propagation of uncertainties, and there's a formula for that. And the formula for that is, this is a function, right? This mean is a function of all of these values. You take the derivative of this function with respect to each of these variables. So all of these variables have some fluctuation. First of all, you take the derivative of all of this function with respect to y1. What do you get? One over n. तरीका से देख लो. You have this function. You know that this function is a function of the variables y1, y2, y3, and so on. Has everyone studied derivatives? Right. So this y bar is a function of all of these variables. So you take, first of all, take the derivative with respect to the first variable y1. The derivative is just 1 over n. You multiply this with the uncertainty in this variable, which is okay. Then I take the derivative with respect to y2, which is 1 over n y2, 1 over n. Multiply this with the uncertainty in that variable. Okay, and then what I do, I take each of these derivatives, I take the square. Derivative multiplied by respective uncertainty. किस वेरिएबल के रिस्पेक्ट डेरिवेटिव लिया उसी की अनसर्टेनिटी से मल्टीप्लाई करना है. सॉरी, अनसर्टेनिटी आमतौर पर पॉजिटिव लिखी जाती है, लेकिन पॉजिटिव नेगेटिव वो ऐड हो जाती है. ठीक है, तो हमने हर एक का स्क्वायर ले लिया और फिर सबको जमा कर दिया. ठीक है, और फिर सारों को जमा करने के बाद स्क्वायर रूट लेंगे। Sorry? Shabash. So this is like you are taking the root of the mean of the square. So you're adding the uncertainties in quadrature. You're not adding them because adding them would just amplify the uncertainty. If you add this uncertainty with this uncertainty with this uncertainty, the number will be very large. But then uncertainties can be bidirectional, positive or negative. That's why you don't want to add these numbers. You just want to take the square and then add. Square makes each of these values positive. You then take the square and then add. It's just like a Pythagoras theorem over a large dimensional triangle. Okay, it's like a Pythagoras theorem over a large dimensional triangle. ये Pythagoras theorem की तरह की चीज है ना. Hypotenuse square is base square plus altitude जो भी वो कहते हैं. ठीक है? So this is how you find out the uncertainty in the mean. Due to the type B uncertainties. So if I simplify this, the uncertainty in the mean, this will be 1 over n u by I square summed over all i's sum, right? This is a compact formula for the uncertainty in the mean. Now this is the uncertainty in the mean due to type B uncertainties. So this is a type B uncertainty in the mean. You already have a standard error in the mean which was a type A uncertainty. Now how do you combine the type A with the type B? You add them again? No, you add them in quadrature. So you take this value, square it, plus standard error that we already calculated, square it, add them together and take the square root. So whenever you have two different kinds of uncertainties and you want to find the overall impact, you just take each uncertainty and square it. Add in quadrature. You don't want to rawly add or barely add uncertainty. You add in quadrature, which means you take the square and then add and then take the square root. Okay, so now this is the uncertainty that has leaked into the mean, propagated into the mean, bled into the mean from the type B uncertainties. So the type B uncertainties have given a certain contribution to the overall uncertainty in the mean. This type B contribution has to be combined later with the type A uncertainty which you calculate, which is standard error in the mean, and you combine them in quadrature and then add together. That will give us the total uncertainty. Okay, so I've done this for you. So and doing this is important, in fact crucial for this data set, because the type B uncertainties go way beyond the standard deviation band. So the standard deviation band does not take into account or account for the type B uncertainties. In the previous cases, the error bars were too small and therefore they would not have any perceptible effect on the final uncertainty. But here they will have not only a perceptible but a significant impact on the final uncertainties. Okay? So now let's see how we can do that, do all of this. So if you look at this piece of code, my uncertainty, each of my u by I is 2% of that y. So I have 2% of that y. I square it, add it to the previous value, then I take this. When I've taken the sum, I take the square root and divide by n. So here I take the square root of this sum and divide by length of it. This gives me the uncertainty in the average value of y due to the type B uncertainties. Finally, and this is 0.07. Remember that the standard error that I calculated due to type A was only 0.01. So I cannot discount the type B uncertainty now. मुझे उसका ख्याल रखना पड़ेगा. It's 7 times bigger than the type B uncertainty. And this is also evident from this graph. This is the standard deviation. The standard error would be even smaller, but these fluctuations in type B are much bigger than the standard error and the standard deviation. So now, and the numerical values also reveal this fact. The type B uncertainty in the mean is 7 times bigger than the type A uncertainty. So now I have to combine the two together, right? And this is my total uncertainty. So I take the standard error, square it, type A. This is the type B, square it, and take the square root. This gives me the total total uncertainty in my data. Okay, so now this is the final data in which I plot the total uncertainty, and this is still not at the 95% confidence level. For the 95% confidence level, I still have to multiply this with 2 or 1.96, or sorry, 2.35 to go to the 95% confidence level. At this stage, I have combined the standard error in the mean due to type A and the uncertainty due to type B, combine the two, and this is the new standard error that I get, which is now bigger than the previous standard error, because it has now been, the type B uncertainties have been incorporated because they are significant. Got it? Any questions?
अगर टाइप बी अनसर्टेनिटीज टाइप ए वाले से कम हो तो फिर हम उसे इंक्लूड करेंगे या नहीं?
कितनी कम हो? अगर आधी हो, 3/4 हो तो करनी चाहिए. अगर बहुत कम हो, 10% हो, 5% हो, तब ना करें. वो पता चलेगा ना स्टैंडर्ड डिविएशन में प्लॉट करके कि स्टैंडर्ड डिविएशन के बैंड से बाहर जा रही टाइप बी अनसर्टेनिटीज या नहीं. और याद रखिए कि हमेशा हो सकता है आपके पास इतना खूबसूरत डेटा ना हो लैब एक्सपेरिमेंट के अंदर, तो आपको इसको जितनी हद्दुल बसा यानी अपनी वुसअत के मुताबिक, अपनी कुदरत के मुताबिक इसको फॉलो करने की कोशिश करना चाहिए इस स्कीम को, इस सिस्टमैटिक प्रोसेस को. ठीक है? तो हो सकता है कि यहाँ पर रोड ब्लॉक्स आ जाए, कोई डेटा अवेलेबल ना हो, फिर आपको देखना चाहिए कि व्हाट्स द बेस्ट दैट यू कैन डू, एंड ऑलवेज state what you do. The measurement outcome really means the best estimate. It means the standard answer, and it means that you have to quote the confidence interval. Otherwise, it's incomplete. Otherwise, वो सिर्फ reading है, measurement नहीं है. ठीक है? तो अब थोड़ी सी एक कर्व फिटिंग की एग्जांपल देना चाह रहा हूँ. कोई और क्वेश्चन? सिर्फ 10 मिनट और कर्व फिटिंग की बात करते हैं.
Multiplied 4 with 0.02 when calculating uncertainty in value y. थोड़ा सा scroll down करिएगा. Yes, there 0.02 times y.
किधर?
Second last minus 4. Yes.
Given error bars, 2% error bars. Yeah. अच्छा, आपको पता है कि एक स्प्रिंग हो, मास और उसके साथ अटैच ऑसिलेटर बन, इट बिकम्स एन ऑसिलेटर एंड द टाइम पीरियड एंड द मास आर रिलेटेड. T is 2 pi square root m over k. Alright, so a student performs an experiment in which he measures puts objects of different masses and measures the time period using stopwatches. And there's a sequence of experiments, repeatably. I mean, he does the same experiment number of times, 6 or 7 times, for different masses. And the goal of this experiment is to find the parameter, which is a spring constant. That's one goal of the experiment. Okay, so now I've compiled data from such an experiment. So we have in front of us so this is a sequence of masses in kilograms, 0.513, 0.581. This is a sequence of time periods in seconds using a stopwatch. Okay? Now we assume the following. We have some type B uncertainties. Each mass is off by 1%, because these masses are measured on a weighing scale. The weighing scale has some finite digital resolution. It has some accuracy as well. So suppose all of these type B uncertainties combine to give a 1% type B uncertainty to each mass. This type B, even without any fluctuations. And the time period is also off. Suppose it's a perfectly accurate stopwatch with infinite resolution, but there is some response time. So the response time is generally about 200 milliseconds. So when the time period is calculated, the watch is initiated and it's terminated. So there's a 200 millisecond uncertainty on each end. So the total type B uncertainty due to the response time is 200 milliseconds squared plus 200 milliseconds squared. You can't just add the uncertainties, because one uncertainty could be positive, the other could be negative. So you add uncertainties in quadrature. That's the rule of the game. And these uncertainties are so big, the response time associated uncertainties, that they are bigger than the finite resolution of the stopwatch, which could be of the order of nanoseconds or microseconds. So you don't want to take that into account. It's meaningless. So now you have type B uncertainties in the mass and in the response time. Okay? So uncertainty in mass, uncertainty in time. And the uncertainties in mass, they're all different, because the 1% of each mass value, they're all different. But the uncertainties in each response time is the same, because each act of measurement, the time is just the same. Okay? So I make an array for the uncertainty of the mass, and for the uncertainty the time, I make an array of the response time repeated the same number of times. Okay? So now what I would like to do is, first of all, the data that I get has this time period and mass. I want to make a plot. The first thing that you ever do after getting all the data, notifying all the uncertainties, is to make a plot. Okay, so let's make a plot. So here I have mass and here I have the time period. But I really need to plot the error bars. So there is some uncertainty associated with time and some uncertainty associated with mass. So there are error bars along the horizontal and the vertical axis. Right? So if I look at the uncertainty, the times or each value, it's about 0.28 seconds for each of these measurements. And the values of t is 1.24, 1.33. So the uncertainty time is about 15 to 20, 25% of time itself. So it's a large uncertainty in time. So if I plot these uncertainties with these error bars, this is the kind of graph that I get. So time, mass. Large uncertainty in time, visually. Small uncertainties in mass. Now if I want to calculate Q or estimate Q, my goal is to estimate in the best possible fashion the parameter for the spring constant K. So in order to do that, I just want to modify this a little bit. So this is an equation and there is a non-linear relationship between time period and mass because there is a square root here. So if I want to do curve fitting, then I really want to linearize this data because it's easier to linearize data and then do curve fitting. So I want to define variables in which there is a linear relationship between two variables. So how would I do that? Just square cut it on sides.
So convert it to this equation of straight line
ठीक है.
y is equal to ms plus 2.
ठीक है. So another way of doing that is t square into k over 4 pi square is m. Right? Okay. So now this shows that I can write m here. If I make a plot between m and t square are linearly related, m and t square are now linearly related. वही वाली बात आपने देखी, मैंने दूसरी तरफ कर दी, स्क्वायर रूट की बजाय मैंने स्क्वायर कर लिया. So now this is a linear function of t square. So one of the variables is mass, the other is I just take the square of each time period and make a graph between m and t square. And the slope of that graph will be k over 4 pi square. So I make a graph and I do curve fitting. I fit with a linear model and find the slope of that model. You've already been introduced to curve fitting in the previous lecture somehow. So if I take this data, this is my non-linear data. What I do next is I define a variable which is the square of t, and then I want to plot on the x-axis. What do I want to put on the abscissa? On the horizontal axis, t square, and mass on the vertical axis. On the ordinate, on the abscissa, I want to put t square. So t squared followed by mass. Now I want to know the errors. I already know what the errors in the mass are. I want to plot error bars. I already know what the error bars in mass are. 1%. But now I need to know the error bar, the uncertainties, not in t but in t square.
It will be multiplied by 2.
तो uncertainty t हमें पता है. तो uncertainty in t square कैसे आएगी? Error propagation formula. Suppose my t square is my function, right? Let's call it z. I know the uncertainty in t. I need to know the uncertainty in z. अब मुझे t square में uncertainty चाहिए ना? तो अब यहाँ मेरे पास single variable है. So the uncertainty in z, which is the uncertainty in this variable t square, क्या होगी? I take the derivative with respect to time 2t, multiply this with the uncertainty in each time. And there's only one variable, so there's nothing else that adds to this. So I take the square and then the square root cancel out. This is my uncertainty t square. So if my time has some uncertainty, the uncertainty, the square of that variable is twice the origin. Okay? So this, I use error propagation to calculate the uncertainty in this variable. In your mind, think that t square is some new variable, which is a function of t, and that uncertainty has bled into the uncertainty in t square. उसके अंदर सरायत कर दी, उसके अंदर घूम फिर के चली गई. So that's why here I have the uncertainty in the x-axis, which is the t squared, is 2 times each of those times multiplied by the uncertainty in that time, ut. The uncertainty in mass is already known, and then I plot. So here is a plot between mass and t square with all the uncertainties properly drawn. Now what I could do, I could fit this to linear data. Okay, so now I do a fitting process. I write a function for fitting. Very easy to do. You've already seen this. This is the function polyfit, polynomial fit, t squared mass. Mass is on the y-axis, t squared is on the x-axis, and polynomial fit of degree 1, which means linear fit. And what do I get out of this fit? I must get a straight line. And a straight line is defined by 2 variables. One is called the slope, the other is the intercept. So I run this function. This function is available in the numerical Python package np dot polyfit. I run this and I get the slope, and I can also get the intercept if I wish to look at it. Okay, so the slope is 0.3255. Now I want to plot the data and I want to plot the fit together. I want to plot the line that has come out of this fitting process, which will tell me what the data looks like, what kind of mathematical model does this data follow. So this, we have proposed that that if you look at this graph here, it seems that a straight line would be a good mathematical model to fit this data. Okay, and we can go more into the mathematics of what this fitting means. It's an optimization process, but there is a straight line that we would expect to be drawn between these means. And the physics of this problem also tells that there has to be a straight line, because this is a linear harmonic oscillator in its low amplitude regime. It's like a harmonic oscillator, and pendulums behave like this. Harmonic oscillators, masses attached to springs, even an electron, 2 atoms that are close together behave like this. So we want to plot a line which is called the best fit line that goes through this data and is best fit in a certain sense, the least squared sense. So this is more mathematical detail, we can talk about it. But when I do this, so I want to plot the line as well. So in order to plot the line, I have the slope and the intercept. I need a continuous stream of points that can allow me to plot the line, the fit line, and superimpose it along with the data so that I can see how good a fit have I achieved. So in order to plot the line, I need variables for that line. So I create a line for t squared, which is just a sequence of points between 1 and 3.5, 100 points, and mass line, which is slope times t squared plus intercept. So this is, I'm defining the line, the best fit line that I've gotten from the slope and the intercept that have been churned out by the optimization process, by the curve fitting process. So this is the equation of the best fit line. Okay, so now what I do, I plot t squared mass, error bars, and I also plot on the same figure the t squared line and the mass line, the lines that I get out from curve fitting. So these are my data points. Okay, sorry. So these are my data points with their error bars. And this is my line, best fit line. Now notice a few things. Sorry, आज का section लंबा हो गया लेकिन इसको करना पड़ेगा और कोई तरीका नहीं. So this best fit line, it's possible that the best fit line does not pass any point. Okay, and it does not touch any point out of all of these points. It might seem that it touches this point, but this point can be slightly off. There are certain properties of this best fit line. It might not touch any point. Number one. Number two, the centroid of this line. The centroid of this line is equal to the average of all the data along the x and the y. So you take all the average along x of all of these data points, average along y of all of these data points. The line passes through that average point. On average, there are as many points above the line as there are below the line. So this line has certain properties. It's called the least squares curve fit line. It's best fit in the least squares sense, which means that if I take the deviation of this point from this point, of this point from this point, of this point from this point on the line, and take the square of these deviations, add, then that value will be minimum for this line. So if I put this on the blackboard, for this line, the line has this form. For a given xi, the line at a given xi has this ordinate mxi plus c. From this, if I subtract the experimental data point, I get a deviation. Correct? Okay? And if I take the square of this, I get a square deviation. And if I add up all of these deviations, I get a sum of squares. And if I then divide by the number of points, I get a mean square deviation. Mean of the square of the sum of deviations. This factor, generally it's called a goodness of fit factor. Goodness of fit. Statisticians call this chi-square factor. This factor is minimized for this best fit line. Then the best fit line by definition is that line which minimizes this parameter. ये deviations, ये इनका स्क्वायर ले लें, ये फैक्टर छोटे से छोटा होगा. इनको रेजिडुअल्स भी कहते हैं. रेजिडुअल्स छोटे से छोटे होंगे. मैं भी आप ग्राफ दिखाऊंगा. तो ये इस लाइन की प्रॉपर्टी है और ये ऑप्टिमाइजेशन और सारी मशीन लर्निंग यहाँ से शुरू होती है. Okay, so this is a property of this line. Now from the slope, you find the slope of this line. Can you find k?
Yes.
You multiply the slope with 4 pi square, you will get an estimate of k. लेकिन अभी जाननी छूटेगी. What is the uncertainty in this slope? This slope will also have an uncertainty. So the parameter that you found will also have some uncertainty in it. How do you find out that uncertainty? Because if you don't quote your uncertainties, your result is just a mere reading. It's not a measurement.
Worst fit line.
Huh?
Worst fit line.
Worst fit line क्या होती है?
जो एक एरर बार के लेफ्ट के एंड से दूसरे एरर बार के राइट के, मतलब जो एक एरर बार जैसे ये पहला वाला है, इसका अगर हम लेफ्ट वाला पॉइंट ले लें और
ये यानी ये एक ले लें और एक ये ले लें.
नहीं ऐसे
ऐसे
जी
ऐसे
नहीं ऐसे और जो पहला वाला
यानी ऐसे
हाँ
और एक ऐसे ले लें.
नहीं ऐसे
ऐसे भी तो ले सकते हैं.
हाँ ऐसे ले लें.
तो एक तरीका तो ये है. ये बिल्कुल ठीक है. यानी there is a band of slopes associated. There is some range of slopes. You can draw multiple lines. I can draw a line like this. So there is this sequence of lines that can be drawn. But there is only one best fit line, by the way. But we need to find out the uncertainty in the slope. And there will be some uncertainty in the intercept as well. So in order to find the uncertainty in the slope, there are formulas which are mathematically derivable, analytical formulas. They can be derived. Remember that at the heart of all of this is the concept of minimization of functions. You know how to minimize a function. You take the derivative of that function with respect to a variable, set it equal to 0. That's how you minimize. So when this curve fitting routine runs, it also minimizes this chi-square function. It takes the derivative of this chi-square first with respect to m, puts it equal to 0, solves this equation together with this equation to find out the value of mmc, the slope and the intercept, will simultaneously solve these two equations. This is how you minimize any function. ठीक है नहीं, आपने पढ़ा होगा कैलकुलस में कि मिनिमाइज कैसे करते हैं फंक्शन को. तो ये जो रूटीन है ना कंप्यूटर की, आप हाथ से भी कर सकते हैं. हाथ से मैंने अपलोड किए हुए डॉक्यूमेंट्स वेबसाइट पे देखें. डेरिवेशन एग्जिस्ट्स ऑन आवर वेबसाइट. Okay, so it's not something really magical that is happening here. So if I want to find out the uncertainty in the slope, what I need to do is I need to get rid of the uncertainties along the independent variable axis. And how do I do that? I need to transfer that in uncertainty to the y-axis. Because that will make my task easier. So some uncertainty will be transferred from the x-axis to the y-axis. Now how do I transfer an uncertainty? You see, again this propagation of uncertainties. If I know the uncertainty in this p square variable, I can find out what uncertainty would it cause in m, because I already know the slope. So the uncertainty in m due to the uncertainty in t square, how can I calculate that? I take the derivative of this with respect to t square, which is k over 4 pi square, multiply this with the uncertainty in t square. This will give me the uncertainty in m due to the uncertainty in t square. Remember that my m depends upon t square. So any uncertainty in t square will map onto m, the uncertainty in m. उसपे cause करेगी ना? It will bleed through from the independent axis to the dependent axis. If this is uncertain, this must be uncertain. So what I'm trying to do now is transferring the uncertainty from the x-axis to the y-axis. And if you want to do that, I just use the same formula that I have for propagation of uncertainties. So I take the uncertainty in t square multiplied with the slope over 4 pi square, I'll get the uncertainty in m. So this is my transferred uncertainty. Transfer, that is M already has some residual uncertainty. So now it gets some additional uncertainty from T squared. Yes, please.
So won't we also have 2t in this, because wouldn't we take the derivative with respect to t?
Sorry, बिल्कुल सही. I'm sorry. Into 2. Exactly. I'm sorry. बिल्कुल ठीक. Sorry. Sorry. ठीक है. So now if I were to do this transfer process, so here this T squared transferred is the original uncertainty times 2t times slope, and I also need to divide by 4 pi squared. In fact, all of this is the slope. K is not the slope, all of this is the slope, so I don't need to divide once again by 4 pi squared. This, all of this is the slope. Okay? So here this is the transfer, and then what I do, I need to square the transfer and the original uncertainty in mass, add them in quadrature to get the total uncertainty in mass. At every stage, I have to do a budgeting, an accounting of all the uncertainties. Alright? Got it? Yes, please.
So it could be do it the other way around and calculate the uncertainty with respect to t by changing the equation and then add it with the.
You can do it the other way around as well, but then it will be slightly cumbersome because then your K will be 1 over slope. And when you have something in the denominator, its uncertainty gets messed up, because when you take the derivative, it gets 1 over squared. So you just want to keep things simple. So now if I do this transfer process and I find the total uncertainty in mass, and then I plot, this is what I get. T squared this is T squared mass, and now the uncertainty in T squared has transferred to the uncertainty in mass, and the uncertainty in mass has gone up quite a bit because of the transfer process. Now this is the same line that we've already calculated, the same best fit line. Now this uncertainty in this slope of this line can be calculated easily from the uncertainty in these points. I don't have to worry about the uncertainty along the x-axis, because now different kinds of lines can be drawn. One from here to here, one from here to here, here to here, and so on. A huge range of lines could be drawn. So we're really finding out the bands on this graph, the confidence intervals on this graph. And now if I want to find the uncertainty, by the way, this is the value of K. And now if I want to find the uncertainties in the slope, there is a formula for that. And where is that formula coming from? Let me show you. It's on our website. Is given by the uncertainty in the slope is given by the data point minus the corresponding point on the line, best fit line, squared, which is the deviation squared divided by d over n minus 2, where n is the number of points. And capital D is defined as how far is a point from the mean of that point. Okay, so I use this formula to calculate the uncertainty in the slope. So this is my small d. By the way, this is a plot of the residuals that I was mentioning. How far is a certain point from the line of the best fit? This is the line of the best fit, and these are the data points. Okay? Got it? And also remember that the best fit line is that line for which if I take the square of this, sum it with the square of this, and take the sum of the squares of each of these deviations, the result would be minimum for this line. If I go to take the line above or below, this chi-square will go up. So it's minimum for this best fit line. So this is the plot of the residuals. Sometimes when you do best fitting, it's really nice to have a look at this plot of the residuals as well. Give you a good idea. See how small these values are, 0.02 between plus minus 0.02. And by the way, if I finally plot the, or kind of compute the uncertainties, now I am also invoking the t statistic. I'm looking at 95% confidence intervals once again. So this is my final result. 12.9 is my best estimate of k, and the uncertainty in that value of k is 0.1 at the 95% confidence level. So I've used the formula to calculate this uncertainty in the slope. Actually, this is the uncertainty in the slope, 0.04. And then I multiply with the numerical factor t, which I calculate from the point percentage function in the same manner. And I look at what the uncertainty in the slope would be at the 95% confidence interval. So this is a wholesome introduction to it covers a little bit of plotting, it covers a little bit of uncertainties. Now next week we'll do a small activity in which you will generate your own data inside the lab. Next time the lab starts at 8 o'clock in the Phys Lab 1.
So we were taking the same horizontal plane here. So how did, if we use this formula of the slope, why did we need to transfer the mass at all?
That's a very good question. So this, at least we know k. We know the best estimate for k. We don't know as yet the uncertainty in this k. That's your question probably. So this transfer will also be uncertain. But this is an assumption that we're making, that if this were the slope, this is the best estimate of the slope anyway. So this is an assumption that we're making, that if this were the slope and the uncertainty would transfer from the horizontal to the vertical axis, how much on average, what's the best estimate of the uncertainty that would be transferred? So this is just an estimate. Now once you have the uncertainty in the slope, you can go back and see if this is a good transferred uncertainty or not. But this is something that is too cumbersome to do and wouldn't have much of an impact anyway. Okay? Right, so inshallah see you next week. Thank you.